这个可能要看，就是它这个应该是就是收音，但是它不会把这个声音 post 出来。
晚上几点钟的飞机啊？
晚上9点多，9点半。
什么航空公司
？Delta。
Delta，那不在一起。我也是晚上走了 UA 的，从复活号出来。
We start.
Should we start?
Yes.
Oh, there's somebody in the Zoom. Let's wait for a few minutes.
Yeah, I think we can wait for like a minute.
So the issue is not that it's too noisy, just that people are. It's the end of the semester. Maybe we don't have.
Still excited.
It's like too happy for people to celebrate the very end of their semester. Yeah.
Man noise coming.
Like should be like the story.
Oh, yeah, sure. Today we will have Zebin as our speaker. He is expert in data science and AI. Let us welcome Zebin and I will give the speech.
Yeah, thank you very much. So for today, my talk is about Daniel, which is the name of our algorithm. And our algorithm is a distributed and scalable approach for global representation learning with EHR applications, where EHR stands for electronic health record. So this work is conducted by me as the first author and our collaborators in Center of a Learning Health System, which is CELEHS over here. And first, we're going to see the overview of the contents. So to start with, I'm going to talk about the research background and a little bit of the motivation over what we are going to do. And second, I'm going to introduce the layout and the pipeline of our algorithm. And third, I have some results over simulation, and we also conducted a real-world EHR data analysis. And by the end of the day, we're going to summarize what we have over here, and hopefully I can reserve some time to answer your questions. So first, we can talk about the background of the multi-institutional data. So multi-institutional data, it would have inherent complexity, and conventional approaches would rely on computationally expensive SVD for high-dimensional matrices until convergence is reached. So basically, our matrix is like 30K times 30K in the minimum. And just imagine like doing SVD on those sides of matrices. Or sometimes we're going to do like tensor decomposition on like plus something, maybe like 100 plus something. So if we're going to do any kind of matrix decomposition on those capacity of data, and we try to like work on the eigenvectors, it could be a big issue. And apparently, the general data layout is that we have this hospital as one of our data. So let's say this is MGB or Massachusetts General Hospital and Brigham and Women's Hospital. And we also have UPMC, University of Pittsburgh Medical Center. And their data, you just cannot hope that their data is interchangeable because these contain too many sensitive data. Like for here, you have the data over whether or not this patient has taken this medication, or whether or not this patient has conducted this or that surgery. So if that happens, the hospitals would not be allowed to share their information with any sources out of their system.
One question.
Yeah.
Because like I'm a probabilist, usually we say IID sequence. That kind of thing.
Yeah.
So if you have the data have two different resources, can you assume they have the same distribution or something like that?
Yeah, so the distribution like within the data set could be different. Okay. There is a likelihood because like, so the Mass General Brigham has like different branches of it. And for some of the branches, like for this branch, it is like more remote hospital, like Newton Wellesley Hospital, which is a local hospital. And this guy could be like Mass General Hospital, which is a very famous hospital. And most of the tough cases will go there instead of going there. So if you like do kind of prediction question or you kind of regress their information on some outcomes, there is a likelihood that for this cohort, you're going to get patients with worse outcomes. But for this, there is a likelihood that you have patients with like less likelihood when the disease is going to have bad prognosis. So there is a likelihood that from different sites or institutions, there is some heterogeneity. And that is another open question that I'm trying to solve in my another paper, which would be available soon. Okay. Yeah, thank you very much for the question. And so to integrate those kind of data sets, where even the transition between here is also heavily regulated, this leaves us a question such that the compliance cost is like very high. And it takes lots of time for us to coordinate. And sometimes those sort of coordination is almost impossible. So let's give you guys a quick example. So this is some of the data sets that our research group would have. So the first of them is BCH, the Boston Children's Hospital. And then we have the Centre Hospitalier Universitaire de Bordeaux, which is a hospital in Bordeaux, France. Yeah, and we have Duke, we have Mass General Brigham. We have a freely accessible MIMIC data set, which is open source technically. We have the University of Pittsburgh Medical Center, and we have the VA or Veteran Affairs Healthcare System, which is a large data set where basically they have thousands of sites all through the United States. So the integration of all these data sets is a tricky question because each of the institutions, they're different. Like for here, in France, we noticed that there has been a large number of non-standard codes, where basically they have the electronic health records, like we know like he has whatever disease, but that code representing that disease is like not even in English. So the harmonization of those data sets is a very heavy task. And we have some standardized EHR codes like the Phi code, the CCS code, the Loink code, and RX norm code for procedures, for diseases, procedures, and surgeries and prescriptions, respectively. However, these codes are not all we have, and we have lots of more data over here, which we have to dive in. So this is one of our existing work, which conducted by Dr. Zhou, who is an assistant professor in Singapore, in NUS in Singapore. I just met him in Neuralibs and we talked a little bit about this project. So for this cool project, it processed the EHR data set that I told before. So for the codified or more organized data set, people would tend to conduct a step of SVD, which basically we can find the eigenvectors. We can take the eigenvectors as the embeddings of each EHR code. And then for rest of the stuff that we don't have an explanation, no matter it is in English or French, we throw it to GPT. Like see, the symbol is for GPT and here is for GPT. And we throw it to GPT and we throw it to pre-trained language models, which is a version of GPT, which is a version of ChatGPT where their algorithm is based upon. And then we get their embeddings, which we hope to harmonize these two information together and use a graph learning based algorithm to calculate the relationship between those nodes and medical concepts to be specific. And in a more realistic example, this is the general pipeline over what are the exact things we're trying to do with our algorithm. So in the first step, these things, like these columns, these are conducted within the hospital system. Like this is conducted like within BCH, this is within Mimic, this is like within France. And you learn the embeddings and the graph features you learn the organized embeddings and use the graph attention networks to get their output embeddings for the organized part of the data. And for rest of the data that we just cannot harmonize, we use GPT to help us. And for here, we have a step of data harmonization such that we take the mean or take the average across the sites, and then we get an aligned version of the outcome, which we concatenate the information or the embedding matrix for here and for here. We put them together and put them into the pipeline to get the inference for us. So this is the general pipeline we're going to do, and I would like to have you guys focus on the pattern such that these procedures have to be conducted separately. And this is something related to the outcome of our research. So to talk about the outcome, we're going to evaluate the items, the connection of those two items. Like in the outcome, we're going to have a graph over here, where this is like code A, and this is like code B. Or more specifically, if this code is serum, iron, or basically how much iron you have in your blood. And this code is anemia, which is lack of blood. And one of its major symptoms is that you don't have enough iron in your blood. So we can expect this edge or the node embeddings of this node and this node should be stronger. And if this node is like, say, this is called, sorry, like this is like lung cancer. So the relationship between anemia and lung cancer is not that direct. So we consider the embedding of this node is less related with the embedding of this node.
Why do you still call it code B?
So the code B is actually anemia, as an example.
He has a lung cancer, you also
It's code C. So like we consider like code A is like more similar to code B, but code A is like less similar to code C. And we're going to evaluate the similarity from the embedding attached to this code with the embedding attached to this code, which we train from the methods I mentioned before, and the embeddings of this code from the method that I explained before. So we expect that this vector is more similar with this vector, but this vector and this vector, they might be a little bit different. And this is the parameter that we use to claim whether or not we recover the relationship between two nodes. So given this concept, we consider what we call a contrastive learning procedure, which is a little bit of jargon over here. But from this graph, this is what we call a positive pair, where we know that those codes have relationship. But these are negative pairs where we don't expect them to have specific relationships. In this case, we're going to capture a little bit more nuanced and complex semantic relationships between the concept embedded in those codes. So in our previous work, our output includes those embeddings and the attention weights assigned to those edges between the codes. So like you can imagine that this edge also has a weight or embedding associated with it. And we evaluate whether or not these embeddings are similar and whether or not these embeddings are similar, which we expect these to be similar, but not between this and that. Yeah, so the area under the curve is a widely accepted parameter for us to evaluate the similarity and relatedness of medical concepts. And I'm going to use that later in my project. So, as I mentioned before, we're going to consider a more constrained scenario where our data is further constrained into we only have the binary data. All we know is whether or not this code presents in people's record within a designated period of time, which usually matches the cadence where people go for follow-up views after they attend the hospital and get a diagnosis. So for example, in Alzheimer's disease, which we care the most about, the distance is usually about 6 months. And the reason why we need a probabilistic statistics model is that we tried to sell the option of doing AI for many of the institutions. But those institutions would have lots of constraints in the upload of patient records to machine learning as a service or graph machine learning as a service, which makes the probabilistic graphical models almost the only viable option. So one of my paper that has been published on ICML, where I am the first author, it has discussed the vulnerability of GNN-based machine learning as a service to adversarial model extraction, which basically, like the model is proprietary, but somebody, by querying some of the nodes and get a subnode, they get a subgraph, they train on the subgraph, and they get a graph that kind of recover the function of the original graph. And all those things accumulate together. We have hundreds of constraints we have on efficiency and data security protection, where the need is that we just have to make sure our clients or the people who pay for our research to convince themselves that our model is safe. They're not going to send message to someone they don't want to, and they want to save some resources. They want to use limited memory. And these
so
are.
You said you train this on GPT model. Will you feed your data to a language model that you have no control?
Like for these models, it is just easier for me to use GPT for comprehension. Actually, those are like locally established, not the commercialized API, but they can establish language models locally on their GPU resources. So basically, a better word is what we call the pre-trained language model, but I feel that to be a little bit too far away from the audience. So I use GPT to like make it easier for understanding. Yeah, and this need that I described over here is not just present in biostatistics. So I'm going to have a very interesting example later about legal research, where law firms are technically independent, but sometimes they have to work together for a case. And the case evaluation is usually of very high stakes. And the lawyers are much more conservative on machine learning application, even as compared with doctors. Yeah, I just went to Neuralibs. I see lots of the people saying, okay, we're going to do genomics AI. We have like very fancy AI plus health, but there's not so much resource on legal AI because those guys are very conservative. So this is a very interesting case. So this man, his name is Baiju Ravindran. I just cannot speak it, I'm sorry. So he steals $533 million because like he borrows that deal of money from American lenders, but all those money has been sent to a pancake house, a pancake restaurant located in Miami. And then he steal all the money and siphon that money to UK. And he himself fled to Dubai and say, no, I'm not going to get back to United States again and face the lawsuit. And this is the law firm that handles this case. And this is the link for the news about what happens with that case, which you guys can follow if you feel interested in it. So if I'm going to summarize what happens over here, the businessman, the cheater, he's born in India. And then he opened Baiju's, an international education technology company, where they have their ads on the previous FIFA World Cup. If you have anything to remember, I hope you guys have. And their company is accused of siphoning a loan of $533 million from the American investigators through a 25-year-old guy, which is a little bit younger than I did, who opens a fund managing firm located in a pancake house in Miami. And then the money is in UK, the cheater, the guy is in Dubai, and he says he's not coming back. So the question is so realistic that suppose that you're my wife, Attorney Liu in Queen Emmanuel, a top business litigation law firm headquartered here in Los Angeles within 15 minutes drive from USC. And how would you determine whether to take this case with so limited experience of doing law in India? You have to work with those India local law firms to keep track over whatsoever. But you just don't have the resource, and the other law firms would not be happy to share any information out of their system.
I'm sorry. When you say, I'm not familiar with the language.
Yeah.
When you say take the case, so
yeah, so take the case means
the lawyer is in the Baiju's side.
No, they are in the lender's side. They're going to keep track on Baiju.
Okay.
They're going to find the money, find the people, find Baiju himself, and anyone that has liability over the money and has relationship with Baiju. Try to track the money back. So like her firm is trying to track the money back, representing the lenders, but this is very long, this is very complicated, and this is not going to be completed without some understandings over the case, which they don't have, but the other people would not likely to share with them, at least in this law firm. So I would like to introduce my framework with its name, Distributed Architecture for Non-Convex Ising-Based Embedding Learning, which is Daniel. And by doing this, I have a well-rounded solution. So first, we only have the binary data. So we use the Ising model, which is a variant of Markov Random Fields. And this is computationally efficient as many of the other models in its family. And we have some theory to support it, the classical theory with less constraints, which we do appreciate. And for scalability, we elaborate the conventional optimizing strategy of the Ising model, as the conventional strategy is based on complex optimization subject to a nuclear norm laws. And we try to upgrade from the conventional procedure as we involve a non-convex bifactored surrogate loss function. Because the original matrix is that big, let's not think about the tensors for now. The original matrix is that big. Like this is our theta. And if we do it like this is kind of U and V transpose. And for this matrix, it's like 30K, like 200, 30K. And if we're going to conduct learning over here.
I'm sorry, in this story, what do the data stand for?
Yeah, I'm going to introduce this matrix later. Yeah, I have a closed form representation over these.
So the data is about
So
that guy, or the data is about other similar cases? The data is about what?
Yeah, so the data is here. I have set the binary data over like kind of 1, 0, 1, 0, 0, 1, hold 1. Sorry, hold A, B, C, D, E, F. This is our data.
Yeah, I mean, but the data stand for or represent some behavior of these guys by you, or it's about some other cases?
Yeah, so in that is about the cases taken by like an Indian law firm that has like this pattern. Okay, this guy is in Dubai, yes. This money is in Dubai, no. And this money is in UK, yes. The money is in Dubai, no. It's like that. So basically, no matter in the law firm question or in our healthcare question, this is a good representation or the only representation that those people would have. Because like in those cases, the legal documents could be like 1,000 pages long. It's okay for us to like find some labels on whether or not it mentions something. But it is like a little bit difficult for us to find specific patterns over here. And because the law firms will not be able to share the code documents except for the verdicts given by the judge, this is all the data that they have for us. And it is the same for healthcare. Like we only know whether or not this patient has this disease, but we don't know, like if the patient has 2 codes of that disease, that doesn't mean that this patient has a worse scenario or worse scenario over this case. Like within a period of time, if they have 2 codes for lung cancer, it doesn't mean that this patient have like more serious lung cancer than someone has only 1 code of lung cancer. Or in a legal document, like whether or not the money is in Dubai, when money in Dubai is mentioned for 1,000 times, this doesn't contain too much more information than like another case that the money is in Dubai is mentioned like 10 times. Yeah. So this is like a very realistic setup, which we have negotiated with the people who have conducted research with us. And very unfortunately, we have to work with the people who have limited understanding of mathematics. And yes or no is the easiest question they can answer. Yeah. And so for the binary data, this is the data we look for. For scalability, we use this kind of decomposition, which better leverages the feature of the data such that the data is low rank. And to comply with the privacy regulations, we would require only one-shot communication of the gradient statistics without sharing any sensitive raw data across the institutions. And this is our model setup, which we can go over here. This gives you some idea over what this parameter theta is representing for. So suppose that we have n samples that are distributed into different little m institutions, like this is our S1, this is our S2, and these are like SM. And this is our sample information, which is represented by X, like X1, X2, X3, X4, X5, X6, which is a vector. And whether or not it presents is the presence or absence of a feature. for one observation of data in that institution. And our true parameter matrix looks like that, where these diagonal parameters measures whether or not this node is likely to present. And this theta k, theta jk, or off-diagonal parameters in this data matrix represents whether or not these could be positive together or be negative together, because -1 times -1 is 1. So this is going to measure whether or not those xj's would happen together. And this guy is going to measure whether or not this specific item or this specific feature is going to present. And we put it to a probability density function, or you can consider it as a likelihood function. So we conduct an objective function, which we have over here, and this theta star, the true parameter, this guy is actually symmetric because A and C co-occurring is the same as C and A co-occurring. So it is symmetric. And as I said, we have some prior knowledge to our data set. We know it's like low rank, which is very reasonable. And the rank is D, which is much smaller than P. In our case, our D is 200. And our P is much larger. And the off-diagonal entries would characterize the conditional pairwise dependencies, and the diagonal entries would represent the individual tendencies on whether or not this feature is going to occur. And from here, we establish a conditional log likelihood loss function, where basically we calculate the probability and take a log at it. We consider both the diagonal and off-diagonal features of this theta, but in practice, we only use the off-diagonal features of that data for our later prediction, because those parameters would represent the link over here. Yep. The diagonal features is kind of the node embedding, whether or not this node is going to occur in someone's report. But the diagonal is going to depict on how they are connected. So, according to some existing literature, the prior work says that it is very plausible for us to do low rank assumption. And we have a rank D decomposition, theta star equals U star V star transpose, where U equals V subject to a sign, which is both basically decompose a symmetric matrix and you take square root over the diagonal. And then suppose that a latent variable encapsulates the essential information influencing the EHR feature occurrence and joint distribution. The marginal distribution.
Sorry, theta star is symmetric, right?
Yeah, theta star is symmetric.
But then U star V star transpose, this is not symmetric. If I take a transpose of theta star, I got VU transpose. Oh, sorry. Yeah. It is symmetric. And you assume it's low rank?
Yeah.
Something I'm missing is on the diagonal, you measure the occurrence of one letter. So it has a higher chance compared to the off diagonal.
Yeah.
That makes this matrix essentially PSD.
Kind of PSD. So we need it to be PSD. And
so why is it low rank? Feels like it's full rank.
Yeah, so we are going to select the specific diagonal values to make the theta star matrix PSD, or at least we can conduct those kind of analysis. So this is like, so basically this theta star is like
you want to say you truncate at some level to make it low rank, right?
Yes.
It's not exactly low rank.
Yes, like the true parameter, yeah. Okay. The true parameter is like some matrix where only the God knows. But in our reality, the resemblance of the true theta star and consider a truncation that makes sense to us is a well-accepted procedure in our field. So that's why once we have those decompositions, where here is the parameters, where here is the code, and here is the code, and we have the code and embedding code. So these are the codes, and these are naturally the respective embedding of the code.
This also give you some sort of clustering of the code into 200 different groups.
Yeah, like these, you can consider these as like PCs, principal components, or eigenvalues, no matter how you think about it. But from this,
Does 200 correspond to different disease or different?
Yeah, usually like they would correspond to different specific semantics or abstracts of it. Usually we can have some interpretation of it, where usually we can check on some of the medical literature to see their correspondence to a disease. But this would depend heavily on our question, because in some of our downstream tasks, we would request to have a closer depict over what does that mean, what does those columns mean in specific, or whether or not it represents a medical pattern. But in some tasks, we're doing prediction and we chase for a better evaluation score, where in those projects, we would take a little bit more time over here and try to figure out, okay, once this code has those embeddings, it's more likely to link this code with a medical pattern or medical feature. So there is a likelihood that one of them representing P feature, or we can use all of them to consider as a code embedding and use them as a whole to predict for a feature. Yeah. Thank you for your question. And then what we're going to do is that, given that we have a loss function, we have a case-specific loss function for this likelihood. For this side, we have like L1, the loss function assigned only to sample within here. And this is L2. And for SM, we have LM.
Isn't this the same form? It's Asian. They are all Asian model. Maybe you have different. You are trying to learn theta, and the interaction form is the same. Why do you call them different objective functions?
Yes, because the differences over here is that they are collecting from different sites. So for this project,
only the NP are different, but others form are the same.
Yeah, like for the parameters, we assume like those diagonals and theta kj's are the same.
Okay.
For this project, we mainly focus on the items, general patterns of those data, between those data, because the data we have has already been kind of balanced. Where just like if we are going to do polls for elections, like we already did some sampling procedure to like handle the sampling bias.
This is like a motivation from statistical physics, right?
Yeah. So this has
beyond the 0-1 code, I can have 0, 1, 2, 3 P.
Yes.
Colors.
Yes.
Then
exactly.
Have a generalization of this.
Exactly. We have generations over this, and as I mentioned, like the Ising model is just a subset. It is a subset over MRF, and lots of the statistical physics research questions are based on that. So this is one of the models that matches with the data formality we have. And also, very luckily, it is easy to compute. It is easy to compute from like a perspective of engineering. Yeah, because if we consider like more different cases and we have a more elaborated description over these data, then we're going to have a much more complex model, and the efficiency in practice would be a major concern.
This difficulty is to get this partition function estimates. This normalize, you make a density proportional to.
Yeah. This kind of pre-processing is one of the keys over why this result would make sense. Yeah, but this has been like worked on those hospitals. Like if you go to the hospitals, you have to request data saying that we need what kind of patterns of data which we hope them to be harmonized with the other hospitals, and we have some criteria to enroll people in our data sets. So like by doing those kind of pre-processing, we're doing as good as we could. But still, no matter how we do hard enough, those medical data would never be perfect. Yeah. Yeah.
So obviously, I'm not familiar with the literature. So here it's your Daniel objective function.
Yes.
So are there alternatives in the literature? And
yes, I'm going to like briefly summarize the literature in exactly the same.
I think in physics, you have so many ways to do that. You just have a lot of spin, and you need to build a probability distribution on spin.
Kind of self-spin.
Yeah, so
like whether or not they're paired or
some interaction function. So this is some quadratic interaction.
Yeah, this is quadratic.
You can go beyond that, arbitrary function.
You can beyond that. And MRF is like very complex field and a fundamental field in statistics related with physics. And there has been lots of the other models. And what we're doing here is just to find the best model for our question. Yeah, but thank you very much for the question. So to tackle the two major questions over my paper, over the whole project, what I'm going to do here is like I designed a distributed bifactored surrogate loss. And so the first part is the loss on the hub, so this is hub. And we use a step of gradient correction such that these gradients are collected from the other sides subject to an initializer. And we use those to correct with the gradient we collected on the first side to involve the information that has been embedded in the other sides. And we consider embedding balancer because this U and V are subject to like alpha times U multiplies 1 over alpha multiplies V transpose. So we hope like the U transpose U and V transpose V are similar, which means that the embedding of U and embedding of V are somewhat comparable. Yeah. And if we look at this, one thing we're going to notice intuitively is that for now, we only need one round of information collection because this part.
I'm a bit confused. U and V should be equal, right? Theta U is symmetric.
Yeah, U and V is equal, or they are equal with just like differences on their diagonal.
If you make UV equal, I can just update one matrix and remove that balanced term.
Yeah, this is
do a symmetric decomposition, not SVD.
Yeah, this is doable, but there are chances that this matrix is like symmetric, but not necessarily PSD. So like if it is like not necessarily PSD, we can still do those kind of decomposition. But there has been like a sign transition.
Yeah, I agree. This loss function is good for arbitrary theta.
Yes.
But restricting to symmetric theta,
yes,
we don't need this balancing term.
Right? Yes. So like technically this balance term is not like mandatory in data filling, but in our theory, we leave this embedding balancer where once we have the embedding balancer, our theory is going to go through. So this is our procedure of optimization. So first, we have a good initialization that is locally on this hub. And we have a decomposition over it. We distribute our initializer to the other sides where this is just a parameter and it doesn't contain anything that could be claimed as sensitive. And then we compute the gradient.
You just mentioned a diagonal exercise, but now U and V are not square?
U and V are not square. U and V are like that.
Oh.
Because like we assume this guy to be low rank. So, or this is like similar to a low rank matrix subject to an oscillation. So in this case, we use those two matrices to depict most of the information, specifically for the off-diagonal information. Yep, without like handling the whole matrix, which would take lots of computation resources.
You wrote a U equal to D times V or something like that.
Yeah, like U times D times V, where D is like diagonal. And like we can take the square root over the diagonal. If it is negative, we just leave it negative. So basically we have like theta equals U
transpose. Okay, never mind.
U transpose. And for this one, if it is negative, you just leave the negative.
Okay.
Yeah, and for if it is not negative, you just take the square root, like U D square root D square root U transpose.
Okay.
Something like this. But for here, I just use like those UV to be a little bit easier to make things easierly to keep track of. And then we're going to have the gradient locally on those local sites and just send the gradient. So this guy is the only thing that we need to.
So you only do one gradient up, send back to S1.
Yes.
That depends on initialization.
Yeah, that
what if I
depends
have
on
a bad initialization?
So in our paper, we designed a very good method locally on this site, and we have a theorem to show that a local initialization would be good enough as long as the number of m is not too big.
Do you assume Gaussian noise or something? Sorry, do you assume the noise to be Gaussian to guarantee the performance is good enough?
Yeah, you can think about it this way. Yep. So obviously, like intuitively, we will recognize that the initialization of this theta hat 0 is very important, which is, but in our paper, in our work, we have discovered a way to prove that this theta hat 0 is a good initializer as it generates from the hub. Like we only need the hub information to get this. We submit this to the other sites and we put it back. Because like for here, we have a rate that is good enough for the general theory to work through.
You still need some assumption that the hub and the other part are similar. Otherwise, it doesn't make sense to transfer those gradients. Right?
Exactly, but this is some of the assumptions that we would have for transfer learning and any sort of learning that based on a layout like this. So for federated learning or distributed learning, like something is like shared and mutually learnable is one of the key assumptions where I recognize this point. Yep. And as I said, the gradient correction term is going to incorporate the global gradient information via this one-shot communication to guide us on further optimization. And the embedding balancer term is going to regularize the magnitude over U and V to protect our identifiability. So basically, if we don't have U and V, then the result has a concern of not being identifiable. But if we have the condition over U transpose U is similar to V transpose V, then the result is going to be identifiable. If we have those kind of pipelines. If we claim this as our U and we claim this as our V. Yeah. So under some of the assumptions aligning with the accepted prior work in statistics theory, our contribution in theory would include first, the statistical rate of our algorithm, where Daniel would preserve the statistical rate despite its distributed and non-convex structure, as it attains the same rate as the classical result for the low-rank Ising model. And further, the validity of our initialization has been shown where the statistical rate over the local initialization on the hub is of lower order as we needed in the proof in our main theorem or the statistical rate. And finally, I would like to introduce the proximity to centralized estimator, where the statistical rate between our estimator and its centralized counterpart, where we just assume that all the model are the same and we can aggregate all the data together in our simulation, we're going to get that the distance between theta hat and theta tilde is closer between their distance, is of lower order than their distance between the truth. So consider on the space, this is our theta hat, which is estimated by our method using convex, using non-convex, and the distributed. And this is theta tilde, where we still do non-convex, but it's centralized. So no matter you do distributed or do centralized, the asymptotic difference between these two are of lower order than their distance to the true problem, than their asymptotic rate to the real theta star.
That means you don't want to do distributed.
No, that means that even if we have to do distributed due to those kind of regulations, we're not losing anything. We're not losing rates.
Oh, you can only do distributed, but the
yeah, we have to do
performance is like
yes
without distributed.
Yeah, exactly. The performance is alike, and we're not going to have something that is out of the ballpark as compared with the case that we don't have those regulations. Yeah, so
the second term, validity of initialization, do you mean you need assumption that the initialization gives you some estimate that's already close?
Yes.
Not quite close.
Not quite close, but
you do this non-convex optimization to get a better rate.
Yes, exactly. Because like if we're having like a randomized initializer for most of the non-convex literatures, the things would not work because they are non-convex and we cannot assume that those can be optimized in the way it's supposed to.
So maybe your initializing will be I do a SVD on S1.
Yeah, we can do an SVD on here, but we can also apply some losses like nuclear norm to make sure it is almost low rank. Yeah, so this step, so that's why we need a separate theorem for here to make sure that our initialization makes sense. And obviously, all these assumptions, all these theoretical contributions are kind of authentic and tied closely to the general pipeline of our research. And this is some of the results of simulation in our study, where we tested the scenario where P is 200 and we have N equals 1,000. And this is the result where the Frobenius norm or error is to compare the theta hat with theta star. And the rest of those methods are baselines that are based on matrix decomposition. Those are based on SVD. And in performance, we have good performance. Our result is reliable in a distributed form. Or for here, if it is 0, then over here, these are the cases where the data is not distributed. And for here, these are the parameters to measure how distributed the models are. Like if we have a higher M, or the cases we have, we're going to have a higher distributedness level. And the traditional theory tells us the boundary is like, the rate is like M is little o of square root of N. This is the classic rate over the distributed level. And this is exactly what we find from here. So like, in some cases, even despite our assumption that we claim in our theorem is not met, our performance still validates the classic rate, which is very good part of our research. And as we claim to save time, we do save lots of time. Just I would like to mention, like these are on logs, these are exponential scale, like this is time 3 times 3 times 3. But still, we can show our superiority in terms of efficiency and saving resources.
So for these results, what's the dimension?
Yeah.
P and D?
Yeah, so this is P. So number of codes, this is P. So
I mean, how large is P and how large is D for these numericals?
I see. For this one, so this one, P is like 200.
Oh, the P is there. Okay.
Yes. And our D is selected from cross-validation. Yes, because we have to find a D that is suitable with our simulated data. And we have like 1,000 samples, which is not a very large number, distributed in these groups, which I'm going to explain in the next slide. So the distributedness level determines the number of simulated institutions, which is fixed over all the sample capacity. And if x equals 0, this means that the data is not distributed at all. And the baselines are some of the traditional convex approaches that we collected from a round of literature review, where SVD on each those P by P matrix is mandatory on each optimization step until convergence. And in our result, the case where x equals 0 supports that the non-convex approach itself works as compared with convex approaches, no matter distributed or not. Even without distributedness, the non-convexity would still give you a better outcome and a saved time. And if we have the distributed layout, our model does handle the result pretty well, as long as the classical rate is not reached. So our results very much align with the theory, with the existing classical theory, despite we have so many obstacles. And we managed to solve our research question, and we validate and persuade, and we potentially persuade the people that the pipeline is working in the way that we claim to. And I would like to emphasize that our runtime is much lower, where we do save the time for the resources. This is just a toy example, and we have conducted much more real-world and simulated data analysis, where the pattern that we save times is observed in all the circumstances that we considered. So finally, we're going to go to the fun part. We conducted a real-world EHR data, electronic health records data analysis, where our data set is the UPMC Alzheimer's disease cohort, and our data is the indicator of EHR code occurrence in the 6-month observation windows to each patient's clinical history. And we have lots of records collected from 2 giant hospital systems. So in our research, we consider P equals 2,142, but it could be larger in some of our other research programs. So for the baselines, we not just consider the conventional baselines, but we also consider the BERT variants, which includes the SAP-BERT, which is a version of pre-trained language model. And this pre-trained language model is going to basically an AI model that analyzes the semantic or linguistic or language meanings of EHR codes, and it generates the embeddings for patients on the codes presented in their EHR. And this is like super easy to implement. Even we can train the high school students to do that. But those BERT variants are not specifically tailored to the question, and we cannot give our hospitals say, okay, we just need an intern to like use BERT or some variants of BERT and your question is solved. No, that's not gonna happen. But however, these language models are widely accepted baselines in our field. Baselines are basically benchmark models that we compare our results from. So in detecting non-relationship pairs, which is this example, we're going to have a higher score in most of the cases as compared with most of the baselines. So SAP-BERT is a little bit better than us on some of the cases, but for this one, the RX norm hierarchy, SAP-BERT is not working at all, but we handle all the research questions pretty well. And if we compare our results to the partial data where we only run UPMC data or only run MGB data, we're going to see that our results would improve, which means our algorithm effectively integrates the information into different data sets where they're not aligned to get combined together for analysis. And finally, I'm going to introduce another downstream tasks that we have, which is the Alzheimer's disease patient phenotyping. So according to the patient's first recorded target code, a patient's record is split into pre-dementia and post-dementia stage. So we're going to predict whether or not the record is going to be given, whether it's before dementia or after dementia. And we're going to evaluate the AUC for this prediction. So we have two metrics in doing those comparison, because our model would give us a theta hat, and this theta hat has those parameters. Those parameters, theta hat ij, can directly be used back to the probability model. We plug that into the Ising model and generate an unsupervised AUC as we compare with the truth. And for the supervised case, for our method, all the convex baselines and BERT variants, we have the U hat over here, or the node embedding. Like the BERT would give you an embedding, which is the U hat over here. And we compare the quality of those U hats, and we train a standalone model based on the feature embeddings, and then evaluate an AUC between our standalone model performances with a true label, which is also widely accepted in our field. And this also follows with prior work within our work.
You are over time by 2 minutes now.
Yeah, I'll be really quick. We're almost there. And of course, here we have consistently outperforming the outcomes, which shows our superiority. So in summarization, we not just formalize the question, we have the obstacles of 1, privacy, 2, efficiency, and we designed a method that is specifically tailored for our research question. And in theory, we rigorously shows that we're not going to sacrifice classical results despite the obstacles. And then in practice, we show our superiority in handling real-world research questions. And that's it.
Thank you for this talk, and thank you for the very interesting examples. It's very nice to let the math people know more about, say, what is the need of the industry or in the real world. Say, it's quite interesting. So I remember you mentioned so hospitals were in French, right?
Yeah, one hospital is in France.
Say, say the language can be different, but French and English, they are both in letters.
Yes.
Well, some languages can be pretty different. They are in symbols.
Yes.
So, do you have some hospitals that do not have a language in symbols?
Yeah, exactly. This is one of the questions we have. So actually, we work with one hospital in Korea. So like lots of codes are like written in Hangul, which is, the Korean alphabets. And for these, one quick solution is that we can throw them into pre-trained language models specifically tailored for handling the designated language. And this is very, very much doable because like for a language like lung cancer or those kind of items, like if it is like something like this in Korea, I don't know, but we just treat it as like a Korean, or maybe like we just do them like Korea. Like these things, like this is like a Korean language, and they still find those language transfer into a token. And this token would kind of link with lung cancer as well.
Oh.
So this is like the thing we're going to do in attention network. This is why people say like attention is all you need. Like they kind of tokenize those language and find people's attention in those languages, collect those and find embeddings for them. And then do the follow-up processes. So it actually makes less mistakes in directly handling those queries by using those attention tokenized and attention networks instead of like we translate through Google Translate and then work on English. So directly working on Korean is going to make it work better.
Oh,
Yeah.
thank you. It's very interesting.
Yeah, no problem. But thank you very much for the question, and I really
have
appreciate
a
it.
math question.
Yeah.
So when in the loss, usually for Ising model, estimating the parameter difficulties is about computing the partition function.
Yes.
So
exactly.
how do you get rid of that in when you train this, when you do gradient on this loss?
I mean,
partition function is hard to, right? You said the likelihood is proportional to something, but
yes.
you really want to maximize the likelihood. That means I need to figure out what is this 1/z constant for every theta.
Yes, I understand your question.
I don't see that in your loss or kind of.
Yeah, this is a very good question. Like for our theory part, we just assume like these are like 1/n. Like we assume like those are evenly distributed.
But then that's not the Ising model.
What?
Then it's not. Oh, so you do approximation. You assume they are constant for all different data. Yeah,
like for those different data sets, what the data we actually get is not the raw data. For this task, those data has not been the raw data.
They have been very precise.
For different theta, the normalization constant is hard to get. That's my point. So you just ignore that normalization constant.
Yeah, that's like.
Is it possible that it's for the real data to like the numerical value can be similar?
See, when you do the loss, you didn't consider the normalization. There's a 1/z somewhere.
Yeah, I think
there's a log theta term.
Yeah.
That depends on the theta. Some term depends on theta that coming from the normalization. So you simplify further.
Yeah, we simplify further.
Simplification.
Yeah. We did simplification.
Estimation in Ising model is hard.
Exactly. So that's why like we use our model in a rather simplified version to make things easier for understanding and also for efficiency. Yes. So I hope like all those philosophy like in our project would give you guys a sense or a philosophy like how the biostatisticians using those models to solve questions that we have in this world. So there's lots of compensation that we have to make. There's lots of obstacles that people would have. And we can kind of find the best tools for them, modify our tools if such modification is necessary, and then solve the questions that we would like to answer. So this is our philosophy. So yeah, thank you very much for that question. Yeah, that's it. That's it for today's session. Thank you very much.